In this video, we're going to talk about quantum numbers. So in 1925, or around 1925, Edward Schrödinger came up with a set of wave functions. So wave functions describe the motion of electron waves over location and time. Wave functions by themselves are not very useful to us. What's more useful to us is the wave function squared, and wave function is described by the symbol here. That kind of looks like a pitchfork. So the wave function squared defines an orbital or a region of high probability for locating an electron. So the orbital, this orbital or region of high probability, is what we actually care about. So these wave equations give us a mathematical solution that we can use to describe the orbital or the region of high probability of finding an electron. And the three integers that we use to describe the orbitals are the principal quantum number n, the angular momentum quantum number L, and the magnetic quantum number m sub L. Now this is an m sub L because there's another quantum number that has an m with a different subscript that we're going to talk about later. For right now, we're going to focus on these three quantum numbers: the principal quantum number, the angular momentum quantum number, and the magnetic quantum number. The principal quantum number n is what determines the size and energy level of the orbital. So the higher the n value, the larger the size, and the higher the energy level. N is always a positive whole number integer, so something like 1, 2, 3, 4, 5, and so forth. They can be never be negative, and they cannot be a decimal. They're only positive whole number integers. So as I mentioned, larger values of n means that we're further away from the nucleus, which means that we're talking about a higher energy level. Sometimes the principal quantum number n gets referred to as shells. So different shells for electrons. The angular momentum quantum number, L, is what defines the three-dimensional shape of an orbital. So L can be an integer anywhere from 0 to n minus 1. So for example, if n is 2, then L can only be 0 or 1. If n is 5, L can be anything from 0 to n minus 1. So if n is 5, n minus 1, that would be 5 minus 1, which is 4. Oops, 5 minus 1, not 5 minus 4. Got ahead of myself there. So if n is 5, 5 minus 1 is 4, which means that L can be anything from 0 to 4. So it can be 0, 1, 2, 3, or 4. L defines the subshell. So the subshells are labeled S, P, D, F, and G. So if L equals 0, we are talking about an S subshell. If L equals 1, that is a P subshell. If L equals 2, that is D. If L equals 3, that's F. And if L equals 4, that is a G subshell. And you will need to know those letter designations for these values of L. So L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F, and L equals 4 is G. The last quantum number, or the third quantum number, not the last one, is the magnetic quantum number m sub L. The magnetic quantum number gives us the spatial orientation of the orbital. M sub L can be anything from negative L to positive L. And the way you can determine how many different orientations there would be is to take 2 times L plus 1. So for example, if L is 4, that means 2L plus 1 is 2 times 4 plus 1. So 2 times 4 is 8 plus 1 is 9. So there are 9 different orientations for the L equals 4 for each of those subshells. Now to actually label the subshells, if L equals 4, M sub L can be anything between negative L and positive L. So M sub L is negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, or 4. So you always have to take the negative of L and go all the way to the positive value. And if you count those up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different orientations for the M sub L subshell. So this table here gives you some allowed values for N and L and M sub L for different shells. So you do not need to memorize this, because if you're given N, you can figure out what L and M sub L should be based on the allowed values that we've talked about. This is just to give you some examples here. And you will not be given this table, you will have to be able to determine L and M sub L for yourself. So that covers the first 3 quantum numbers. We still have one more we need to talk about. So if you think back to line spectra, if we look at the line spectra of hydrogen, not all of the spectral features can be explained by the 3 quantum numbers we've already talked about. If we look at this line spectra that's at 656.3, if you zoom in on that, that's actually a doublet. There's actually 2 lines there. So the question is, how do we get doublets? Well, the way that we get doublets is there's actually 2 electrons. And those 2 electrons have different spins. There's an up spin and a down spin. So we have another quantum number to describe the spin, which is m sub s. So we describe the spin as positive 1/2 or negative 1/2. Those are the only 2 possible values for m sub s. So m sub s is our 4th quantum number that gives us the electron spin. So with this 4th quantum number, we now have a complete set of quantum numbers. The Pauli exclusion principle tells us that no 2 electrons in an atom can have the same set of 4 quantum numbers. So you can have 2 electrons that have the same value for N, the same value for L, and the same value for M sub L, but they would have to have different values for M sub s, because all 4 of the quantum numbers cannot be the same. So to give you some examples, we talked about that some of the quantum numbers predict the shape or the orientation. So let's look at what some of those shapes and orientations are. So an orbital shape describes a region where we have a high probability of finding an electron. And sometimes we call those orbital shapes lobes. A node is a region where there's zero probability of finding an electron. So with each value of L, the number of lobes doubles and you get one more node. So let's look at some actual orbitals and see what that actually looks like. So for example, S is actually a circle. And we're showing you only a quarter of the circle so that we can show you where the nodes and where the lobes are. So in our 1s shell, we have a node here at the center, and then we have a lobe around it. And as we get bigger, we increase the number of nodes. These green areas that I'm marking in red are actually nodes. So one of the nodes is kind of fairly obvious. It's right here at the center of the atom. And what is at the center of the atom? Well, if we think back to our model of the atom, the center of the atom is the nucleus. So one of the nodes is at the nucleus. We're not going to find an electron in the nucleus of an atom, so we can know that that's one of our nodes. When we get to a p orbital has three different orientations. So we have three different p orbitals. We have a 2px that goes horizontally, a 2py that kind of goes diagonally, and a 2pz that goes up and down. And for each of these, the nodes would be at the nucleus. So if you put all three of those together, this is what you get, this composite view on the end. The d orbital has 5 different orbitals. So we have 5 different orientations here. And you can see the 5 different orientations for a d orbital. So let's look at an example here. We want to write the set of quantum numbers that describes each electron in the 3 2p orbitals. So the first question would be, how many electrons are in a p orbital? So if we go back, we'll write it on this slide here. So we said L equals 0 is an S shell. The S shell can hold 2 electrons. L equals 1 is a P shell. The P shell can hold 6 electrons. L equals 2 is a D shell. The D shell can hold 10 electrons. L equals 3 is an F shell, and that can hold 14 electrons. So if we go back to our question here, we want to write the set of quantum numbers that describes each electron in the 3 2p orbitals. So a 2p orbital, a p orbital holds 6 electrons, and the number before this gives us the value for n. So I'm going to make a table here. And I'm going to make a row for each of my electrons. And we want to write the set of quantum numbers, so we want all 4 quantum numbers. So if we're in the 2p orbital, that means n equals 2 for all of these electrons. And if we're in the p orbital, that means that for p orbital, we said that L equals 1. So that means all of these have an L value of 1. So now we come to m sub L. So if L is 1, m sub L can be anything from negative L to positive L, which means that we can have negative 1, 0, and positive 1. So we've got 6 electrons and 3 values for m sub L. And since there's only 2 values for m sub S, we can't have more than 2 electrons with the same value for m sub L. So I'm going to give the first 2 a negative 1, the second 2 a 0, and the last 2 a positive 1. So between those two, first 2, we know m sub S can only equal negative 1/2 or positive 1/2. So I'm going to call one of these positive 1/2 and the other negative 1/2. And I can do that for each pair. So that gives me 4 distinct quantum numbers for each of these electrons. So we will stop here and we will get some more practice with this in class.